Hello. Today we'll talk about equations of surface. Our previous discussions were very geometric and rely very much on pictures and diagrams and geometric arguments. But in applications, one usually finds that working with equations, or now with the advent of computers, numbers, is in many ways more effective, especially when it comes to specific problems. So you will notice that so far we have not yet introduced the coordinate system in the ambient space. But today we'll talk about the coordinates in the ambient space and how the coordinates on the surface relate to the coordinates in the ambient space. And those relationships are called the equations of surface. And the primary object would be the partial derivatives of those relationships, and that's called the shift tensor. So that's the subject of today's discussion. And that is why this fantastic sculpture by Gary Zayon is back with us, because it really shows an embedded surface in a Euclidean space and gives you a feeling of a coordinate system in the ambient space. Now, once again, this coordinate system looks like a Cartesian coordinate system, and that's a good choice for the sculpture. We will focus on general coordinate systems. Not at any point in our broad discussion will we assume that the ambient coordinate system is Cartesian. Okay, so let's start with equations of equations of surface, and see what utility we can draw from those equations. What are equations of surface? So, to keep in mind is, let's consider a circle. In the plane, let's refer to Cartesian coordinates in this particular instance. In that case, the circle is r cosine alpha, r sine alpha. An ellipse would be 2 cosine alpha, 1 sine alpha, or a cosine alpha, b sine alpha. Those are the two coordinates. If we go to 3 dimensions, now we need 2 surface coordinates. And for example, an ellipse, or let's start with a sphere, would be r, a parameter, just a parameter, r sine theta cosine phi, r sine theta sine phi, and r cosine theta. I hope I got those right. So those are equations of surface. So now let's write them down generally. So let the coordinates on the surface be S1 and S2, or collectively S alpha. And the coordinates in the ambient space be Z1, Z2, and Z3, or collectively Zi. And let those be related by the following 3 relationships. Zi equals 3 functions of coordinates. So this is a very compact way of writing that x is some function of theta and phi, y is some function of theta and phi, and z is some function of theta and phi. Or in 1 dimension, x is a function of alpha, and y is a function of alpha. So this is a triplet in 3 dimensions. Let's focus on 3 dimensions. It's easier to visualize and to see the full generality. So this would be 3 equations, in other words, 3 functions of 2 variables each. And these are called the equations of the surface. Now, when we have an identity, our first instinct is to differentiate those identities with respect to the independent variables. We don't have identities here, we just have functions of independent variables, S1 and S2. And again, going all the way back to how to interpret tensor relationships, is to realize that Zi on the left and on the right represent 2 different things, really. So Zi here, on the left-hand side, refers to our 3 coordinates in space. It might be x, y, z, or r, theta, phi, or any other arbitrary coordinates in the ambient space. These Zi's, Z1 and Z2, are 3 functions of S1 and S2. Z1, Z2, and Z3 are 3 functions. And of course, there is a clean match between those functions and the coordinates. That's why we use the same letter, and don't overuse letters and risk running out of letters. So there we go. That's what these things are, and these 3 functions can each be differentiated with respect to each one of these variables, giving us a 3×2 system of numbers. You can think of it as a 3×2 matrix. And the entries of the matrix are dzi ds alpha. dsi ds alpha. So 6, this is 3×2 values, a total of 6 values. Each one of these functions differentiated with respect to each one of its independent variables. And this is denoted by this symbol that has both ambient and surface coordinates, ambient and surface indices. And this is called the shift tensor, and it's the last object, I think, denoted by the letter Z. Shift tensor. Shift tensor. So, for the next half hour or so, we'll do nothing but discuss the property of the shift tensor, which are many and very important. In fact, it's really, the embedding is really all about this object. So this object is pretty much, this object in its derivative pretty much gives us all of the characteristics of the surface that we're interested in. And in a way it's more effective than what we've discussed before. Before we would differentiate the position vector and have the coordinate basis on the surface, which is a very valuable object geometrically, but it's hard to work with in specific problems because talking about pictures has many advantages but also has great limitations. So the analytical approach eventually takes over, and now's the time when it does it for us. Okay, important point number 1. Shift tensor. Why is it a tensor? And in what sense is it a tensor? So let's answer that question. In what sense is the shift tensor a tensor? Remember, an object is a tensor when it changes according to a very specific rule under a change of coordinates. Here we have 2 different coordinate systems that can be arbitrarily changed. One is the ambient coordinate system, Z1, Z2, and Z3, and we also have a surface coordinate system, S1 and S2. And both of those systems are subject to change. And in the spirit of tensor calculus, we do not specify any special properties of any of those coordinates. Both of those coordinate systems can change arbitrarily. We can consider an alternative ambient coordinate system that is somehow related to the original, quote-unquote, original ambient coordinate system. And we can consider an alternative coordinate system on the surface that is also related to the initial coordinate system. We've been using the term old and new. The new coordinate system is somehow related to the old coordinate system. The new coordinate system is somehow related to the old coordinate system. And of course, both of these relationships can be inverted. We can express the old coordinates in terms of new coordinates, and on the surface the same thing, the old coordinates in terms of the new coordinates. So with respect to which coordinate changes is this a tensor? And the answer is with both and simultaneous changes of coordinates. And I think once I prove, in a moment I will prove that it's a tensor, very simple application of the chain rule, you will just understand the question a little bit better. So the answer will help you understand the question. So here's the answer. Let's consider the values of the shift tensor in the new coordinate systems. So we will refer the ambient space to the new coordinate system Zi prime. And on the surface at the same time we will choose a coordinate system S alpha prime that's different from the previously chosen coordinate system. And we'll compute the shift tensor according to the same variant rule. We will differentiate the equations of surface. So with the choice of new coordinates, our surface will also be described by some equations. Those equations might look very different from these equations, but nevertheless, there will be a new set of equations that describe the same surface, but with respect to different ambient coordinates and with respect to different coordinates on the surface. And those equations will give us the new ambient coordinate systems as some functions of the new surface coordinate systems. Just think about the sphere. I already mentioned what the sphere looks like when the ambient coordinates are Cartesian and the surface coordinates are the standard angles theta and phi. Now let's pick spherical coordinates in the ambient space. Then the equations become r is just a constant, maybe capital R. Theta corresponds to the angle, let's call it theta 1 on the surface, and phi corresponds to the angle phi 1 on the surface of the sphere. So instead of cosines and sines, we now have very simple linear functions, and it just goes to show that perhaps spherical coordinates in the ambient space combined with spherical coordinates on the sphere itself, the two spherical coordinates on the sphere itself, could be the perfect combination for describing the sphere analytically, because the equations are so simple. Some other things become a little bit more complicated, but maybe it's worth it. Depends on the problem. Okay, so the new shift tensor, Zi prime alpha prime, would be obtained by the same rule. Except now we're differentiating these new equations with respect to its new independent variables. And our goal is now to relate these values, these 6 values, to these 6 values, the values that were obtained by the same rule with respect to the old coordinates. And of course, as always, that relationship is obtained by writing down a very careful identity that involves these 3 equations, maybe 4, or their inverses, and differentiating the resulting identity by the chain rule. All right, let's see. So here's what I'm going to say. That Zi as a function of S prime, S alpha prime, S1 prime and S2 prime, can be obtained the following way. We could express these new coordinates in terms of the old coordinates. That's using these equations. Plug into the new coordinates how the new coordinates, plug into the old coordinates how the old coordinates depended on the independent variables on the surface. In other words, plug in this equation, the equation of surface. Let me write this down. This is the equation of surface. Equation of the surface. It should really be equations. I'm not, in tensor expressions, I never know whether to use plural, because one of the points of tensor calculus is to combine equations into one. So this does represent 3 relationships, but maybe it's a single equation. So let's be truer to the spirit of tensor calculus and call it the equation of surface. All right. And then plug in how the old surface coordinates depend on the new surface coordinates. There we go. So this simple relationship can be expressed as a combination, as a double composite function. So this is the difficult step. It's comprehending and wrapping your mind around what's going on here. You can go back to, I think we had a lecture called change of variables, and then we introduced the tensor notation for this very problem. If you review those lectures, that will help you understand exactly what's going on here, which is ultimately not very complicated, but the notation is so compact and contains so much in so few letters that it might be confusing. So I invite you to revisit this kind of calculations from earlier on to really be in command of what's going on here. And what's coming next is, of course, a repeated application of the chain rule. Because in order to evaluate this derivative, we have to differentiate dz, we have to differentiate zi prime with respect to zi, followed by zi with respect to s alpha, followed by s alpha with respect to s alpha prime. So maybe I'll continue here. So the conclusion comes exactly where we want it to come. So dz I prime dzi. Here's how the chain rule rolls. dzi ds alpha, and finally ds alpha ds alpha prime. And look what we have here. Let's move the sculpture in case it's in the way. What we have here is, let's extract the shift tensor in the old coordinates. Zi alpha. And then find here the Jacobian of the coordinate transformation in the ambient coordinates. Ji prime I. And this is the Jacobian of the transformation of the surface coordinates. J alpha alpha prime. Alpha alpha prime. So this is what it means to be a tensor. And this is where the use of the word mixed is most appropriate. It's a mixed tensor. It's a tensor with ambient as well as surface components. And it is a tensor if each of the indices transforms according to its own Jacobian. The ambient index translates according to the ambient Jacobian, and the surface index transforms according to the surface Jacobian. So that's what it means to be a tensor, and it also shows that the shift tensor is indeed a tensor of one contravariant ambient order and one covariant surface order. So we have our first mixed tensor, and it's a big one. And now it immediately, a lot of interesting questions arise. What it means to contract with this tensor. What happens when you contract the tensor with itself? For example, zi alpha, zi beta. Of course, we can juggle the indices because we have shift tensors in the ambient space as well as on the surface space, but it's all of these contractions that are very interesting. And all of them are very meaningful, and we're about to turn to that topic. Okay, let's talk about the shift tensor and many of its important geometric properties. So, central to the geometric interpretation of the shift tensor is this question. Suppose you have a plane and a basis in that plane, S1 and S2, a pair of vectors. And then another vector, U, that is not in this plane, that's pointing out of the plane. And we consider V its projection onto its plane. So V is the orthogonal projection of U onto the plane spanned by the two vectors, S1 and S2. So V, by virtue of being in the plane, can be represented as a linear combination of the two basis vectors. V1 S1 and V2 S2, so its components are collectively V alpha. And the question is, what is V alpha in terms of U and the two basis vectors? What are the components of the orthogonal projection of U onto the plane? And it turns out that V alpha, it's a central problem. I wouldn't call it a central problem in linear algebra. It's an important problem in linear algebra, and it's a simple problem in linear algebra, and it's actually best treated in tensor terms. And I will make sure to talk about it in the very near future. But for now, I'll just give the answer. And the answer is almost what you might expect. That V alpha equals U dotted with S alpha, the contravariant. basis vectors. Just a very, very simple formula. So V can actually be written in this quite elegant way, that V equals U dotted with S alpha. That's V alpha, and then contracted with S alpha. This, I think it's a quite elegant expression. So this S alpha next to S alpha is kind of like the projection operator in a way. So you'll see. So of course we cannot put S alpha next to S alpha here because the dot sort of gravitates this symbol towards U, and these two don't mix. And of course there are many efforts have been made to define what S alpha S beta means just as a pair. But I think in the framework that we've created, it's really an idle direction to pursue, so we won't pursue it. So just remember this expression, and it'll be helpful in what we're about to discuss. Okay, now there are very many ways of to approach what I'm about to say. Very hard to pick the perfect starting point. So let me pick the following as the starting point. You'll remember that S alpha, the covariant basis, is defined as the partial derivative of the position vector as a function of the surface coordinates with respect to the independent variables. And of course, R, this is R when we look only at its restriction onto the surface. But this R, of course, is defined in all of space, so this relationship can be written as a composite function. R is a function of the ambient coordinates, and plug in the equations of the surface. Plug in how on the surface the ambient coordinates depend on the surface coordinates. So very similar to something we did just a few minutes ago. And now applying the chain rule, and we will have, well, we might as well write down what we'll have. dr dzi d alpha, ds alpha. And this, we'll write things again in the opposite order. This, of course, is the shift tensor. There you go. The shift tensor makes its second appearance, and a very natural, we see how naturally it arises in calculation. So before we just defined it, but now we see that there is no avoiding the shift tensor. It really dictates all the action. And dr dzi is, of course, the ambient covariant metric tensor. Excuse me, ambient covariant basis. All right, let's summarize what we just found. We just found this identity. Okay, I don't have to explain how nice and elegant this identity is. But what it really shows is that the shift tensor relates the ambient basis and the surface basis. It relates these two bases. It can also be thought of, it really expresses the surface basis, in other words, the basis for the tangent plane, in terms of the ambient basis. The reverse relationship was not possible, of course, because there are only two of these and three of these. So anything in the tangent plane can be expressed with respect to the ambient basis. But anything not in the plane cannot be expressed in terms of the surface basis. So this can only work one way. It is not possible to express the ambient vectors in terms of the surface vectors. But it is very easy to express the surface vectors in terms of the ambient vectors. So, and these, of course, the entries of the shift tensor are the components. They're merely the components of the surface metric of the surface basis with respect to the ambient basis. So you can almost think of this as two sets of triplets. Rather than a 3 by 2 matrix, two sets of triplets. And each one of those triplets is the components of the basis, of the surface basis with respect to the ambient basis. And speaking loosely in a way that I don't like, but maybe it's good to mention once, you can almost think of those triplets as the basis vectors. I discourage you from expressing any basis vectors in terms of some other background coordinate system. But here's one instance when it's natural. And we can really identify each one of the two triplets when alpha equals 1 and alpha equals 2. We can really call those triplets the surface basis. Why? Because it's the surface basis as expressed with respect to the ambient basis. There is a very natural, not arbitrary background coordinate system. Okay. And of course, being the components of these vectors with respect to these vectors, it can be expressed this way, which is accomplished algebraically by dotting both sides of this identity with Zj, the contravariant ambient basis, and then renaming J back to I, and we would have this identity, Zi dotted with S alpha, which is an explicit expression for how to obtain the entries of the shift tensor, but when the derivatives have already been taken, so you don't have to do any more differentiation. So just pairwise products of these two bases. It's almost like a cross-spatial metric tensor. That's what this really is. Because remember, the metric tensor is when you dot the basis, the elements of the basis with themselves. But here, one of the basis elements come from one basis and the other comes from another basis. So it's sort of like half and half metric tensor. That's another not bad way of thinking about it, but maybe it's not so great. Just take this expression for what it is. Okay. So I think this is beginning to help you understand the geometric importance of the shift tensor. It's really relating objects in the ambient space to the objects in the tangential plane. That's really why it's called the shift tensor, because it shifts things from space onto the plane. Let me show you two more calculations. We haven't talked about the importance of this. This is coming in a few minutes. But let's talk about yet another application of the shift tensor. And I have just enough space here to talk about it. And imagine a vector. U and V are used up here, so I'll use another letter, A. Let me pick a better letter. W. A vector W in the ambient space, in the tangent plane. In that case, W, because it's in the tangent space, can be expressed as a linear combination of the surface basis. There you go. But being in the tangent space, it also means it's in the ambient space. So it can also be expressed in terms of its components in the ambient space, in terms of the ambient basis, coordinate basis, covariant basis. So here's the question. For a vector that lies in the tangent plane, what are its components? And we have its components in the surface. What are its components in space? Remember, that going that way is always possible. For anything that's in the tangent plane, we can express it with respect to the surface basis as we did here. But because it's also a member of the overall space, it should also be expressible in terms of the ambient basis. And if we know these coordinates, which is really the purest way of giving W by a set of numbers, what are its three coordinates in the ambient space? And the answer is very simple. Just remember this identity and plug it in. And what we have is W alpha times Z I alpha Z I. And now all I have to do is place parentheses around this. All I have to do is place parentheses around this. And realize that this is the number, or the triplet of numbers, that multiplies the ambient basis to give us the vector. So these must be the coordinates of this vector with respect to this basis. So this right here is Wi. So in order to go from surface coordinates to ambient coordinates, you just have to contract with the shift tensor on the surface index. So that's, and you're once again beginning to see why it's called the shift tensor. We've just related the surface coordinates of a tangent of an object in the tangent plane to its ambient coordinates. That way is possible. Going the other way, of course, is not possible. If you take a vector in space, you cannot even ask the question of what are its components with respect to the basis on the surface or on the tangent plane, because it's not expressible in terms of those bases, in terms of those vectors, because it doesn't lie on that plane. So we're not even able to ask that question. But we're able to ask the question of what are the components of its projection. So that's the question I'm going to answer right after I erase the board, and of course it will be all about this. All right, let's see what happens. Suppose we have a vector u in the ambient space, and its components are ui. The interesting question is, what are the ambient coordinates of its projection? So we have the ambient coordinates of the vector itself. We want the ambient coordinates of the projection. Of course, we can also find the surface coordinates of the projection, but that would be answering the question in a different way from which it was asked, which is useful sometimes, but now let's ask the question in the abstraction. What are the ambient components of its projection? So from that formula, its projection is given by dotting the vector. Once again, I haven't justified this formula yet. Dotting it with a contravariant basis, and then that gives us the components with respect to the covariant basis. Now let's plug in the fact that u is ui zi dotted with S alpha. Okay. And let's recall that S alpha is Z, now I need a new letter, J alpha Z I. ZJ, excuse me. And let's see what happens. So I don't think I need parentheses anymore. Well, in a moment I won't need parentheses anymore. I needed parentheses here because without the parentheses we have two vectors next to each other and it's a confusing symbol. In a moment, now that we notice that what we have here is the shift tensor with the Latin index lowered and with the surface index raised. Right, so it's kind of now behind the scenes because I'm assuming that we have full mastery of the tensor notation. And because previously we've defined the metric tensors and the either inverses, the contravariant metric tensors, we should be comfortable with index juggling. So maybe it's an exercise, maybe it's not 100% clear, only 99% clear. But when you consider this product, right, it's very similar to this product, but with this index lowered and this index raised. So the result will be the same object, but with the Latin index, the ambient index lowered, and the surface index raised. So what we'll have is ui zi alpha z, excuse me, forgot exactly what I just said. Zi on the bottom, alpha on top, and then it will be followed by z j alpha z j. So that's the expression for the projection, zi alpha. Okay? So what we see right here, are the components of the projection of U. This is the projection, and these are its ambient coordinates. You can call this VI. Right, these are the ambient components of the projection. So they're obtained by contracting with this very interesting object. That should be called the projection. This is really the projection operator onto the tangent space. Because this is the component of the vector itself, and this is the component of its projection. So let's write it down as, define it as P. I'm renaming indices just because I like things in alphabetical order. Pij equals Zi alpha, Z alpha J. This is the projection operator. Let me say a few words about this projection operator. If you think about it as a matrix, it'll be a 3 by 3 matrix. Does it have any chance of being invertible? And the answer is no. Because the way it's obtained from these two matrices, I'm now inviting you for a change to think about contraction as a matrix operation. What it is a 3 by 2 matrix multiplying the 2 by 3 matrix. So these are the shapes. And how do I know that? Because the contraction is over a surface index. So the contraction is over the dimension that's too long. It's over the shorter dimension. So when you rewrite it as matrices, it would have to be a product of this shape. So we're only finding linear combinations of 2 different columns. So even though the answer is 3 by 3, it's 3 different linear combinations. It's 3 different linear combinations of just 2 linearly independent columns. So among the 3 columns of the resulting 3 by 3 matrix, at most 2 will be linearly independent. So that matrix is not invertible, which is really characteristic of all types of projections. So that's one property of this matrix. Another one will appear in 5 minutes. I will once again pause. I will now erase all of this and talk about the relationships between the ambient and the surface metric tensors, and you'll see the relationship with this expression. Okay? As you will see in a few minutes, later on, I realized that I forgot to mention something here. And here's what I forgot to mention. If we just focus on this expression, what this is the surface component of the projection of U onto V. What we did later on right here is the ambient component of the projection of U onto the tangent plane. But just as interesting, even though I mentioned that it's a question in a different form from which the answer was asked in, what is the surface component of the projection of U onto the tangent plane? And the answer is right here. In other words, it's right here. Let's denote this by V alpha, very appropriate. Vi is the ambient coordinate of the projection. V alpha is the surface component of the projection. And we see right from here, this is Zi alpha. So V alpha is Ui times Zi alpha. So the shift tensor in and of itself can be thought of as projection onto the tangent plane. Whenever you contract on the Latin, you give it anything and you contract on the Latin index, that's the projection of that object onto the plane. It's just that the answer is given in terms of the surface components. And if you want the answer in the same form as the question, then you have to take its answer in terms of surface components and do what we did before, which is go from surface components of a surface object to the ambient components of that surface object. And that's done by contracting, once again, with the shift tensor on the free Latin index. All right, and that's how you'll end up with this expression. So this right here is the surface component, and then surface component is translated back to the ambient component, and then of course we can look at these two elements combined into a single object and think of it as the projection operator. I will now pause, erase this part of the board, and just say a few more things about this as the projection operator. Okay, let's discover the relationship between the ambient and the surface metric tensors. A very quick and simple calculation with very important implications. So we know that S alpha beta, the covariant metric tensor on the surface, is defined as the pairwise dot product of the covariant basis elements. And of course, each one of these can be expressed in terms of the shift tensor and the ambient coordinate basis. So there we go. This one is Zi alpha Zi. And then as you know, the dot can go anywhere. And this would be Zj beta Zj. And what we see here is Zi, excuse me. And what we see here is Zi dotting Zj, which of course is Zij, the metric tensor in the ambient space. So the result is, I might as well summarize it here. S alpha beta is Zij, the covariant metric tensor in the ambient space. Zi alpha Zj beta. Okay, so that's the relationship between the ambient metric tensor, between the ambient metric tensor and the metric tensor on the surface. Now that we can almost think of these objects as projections of the shift tensor as affecting projection, we can say that, I'm just realizing something I should have said previously, which I will add after this. So we can interpret this expression as saying that the surface metric tensor is the projection of the double projection of the ambient metric tensor onto the tangent plane. Now let's talk a little bit about index juggling. Of course, you can think of, you've noticed that metric tensors usually don't appear explicitly. And the same will be the case here. So let's think of this contraction on J as lowering the index J, in which case we may write S alpha beta equals Zi alpha Zj beta. What did I do? Wasn't thinking. Zi alpha Zi theta. Okay. And finally, just for reasons of aesthetic, let's raise beta up on both sides. And of course, we will recall that raising an index on the shift tensor gives us the Kronecker delta. So what we'll end up with, I'll switch the orders and I'll write the result here. Zi alpha Zi beta equals delta alpha beta. So here's what we have in this case. So a similar relationship to this one, but here we were contracting on the Greek index, and here we're contracting on the Latin index, which in matrix terms looks like this. We're now contracting on the longer of the two dimensions. So the result is 2 by 2 And not only is this matrix invertible, it's actually the identity matrix. So, two very different things. When we contract on the Latin index, on the ambient index, all we have is just a different formulation of the relationship among the metric tensors. This, remember, is completely equivalent to this equation. So all this really tells us is the relationship between the ambient and the surface metric tensor. It doesn't look that way because here we don't see the metric tensor. We don't see the ambient metric tensor, and we don't really see the surface metric tensor. Nevertheless, those tensors are absorbed in the placement of indices. That's the power of the tensor notation. And this expression is just an equivalent form of this expression. All it is the relationship between the metric tensors. This is something completely different, even though it looks very similar. This is all about the projection. So just keep that in mind. And there you go. This completes this segment, the relationship between the bases. And I wish I could spend more time on this. It's just that with tensor notation, everything is so quick and so smooth and elegant that I really don't have anything else to add, except, of course, these identities are extremely fundamental and more than fundamental. They're just completely basic and really go to the essence of the differential description of surfaces. Okay, I will now pause, finish what I wanted to say here so I can add it later, and we'll move on. Okay, let's continue talking about projections. I have a few more things to say about projections. Projections have the property that if you project something twice, in other words, you project a vector and then you project the projection, the second projection does nothing. So projecting something twice is equivalent to projecting something once. So a projection followed by a projection is equivalent to a single projection. So let's see if this object has this property here, and it's just a nice exercise in working with the shift tensor. Okay, so a projection followed by another projection would be something like this, the product of the corresponding matrices representing the linear transformation. And then let's recall the expression for each one of these projections. This is Zi alpha, C alpha j, and this would be Z, I j, and now I need a new letter, beta, Z beta k. And what do I see now? I now see this combination right here, which by the relationship between the metric tensors is the Kronecker symbol. This is delta alpha beta. And of course, it will just serve to rename beta into alpha or alpha into beta. Let's rename beta into alpha, and we'll end up with Zi alpha, Zi alpha, Z alpha k, which by this definition right here is simply P I k. So indeed, applying k twice is the same as applying k once. This can be written in matrix notation the following way, which of course suggests that the two or however many eigenvalues satisfy this equation. So they're all either 0 or 1, characteristic of all projections. So that's it. That's it for that question. Let's now spend a few minutes talking about the projection onto the normal. We've talked about the projection onto the tangent space, which is n-1 dimensional if the ambient space is n-dimensional. Now let's talk about the projection onto the normal, the one-dimensional projection. The projection onto the one-dimensional space. And just looking ahead by just a little bit, if we take a vector and project it onto the normal line and to the tangent plane, onto the tangent space, and you add those two projections, you get the vector back. That should be clear geometrically. If it's not clear, that's definitely something to think about. If you have two orthogonal spaces and you take a vector, project it onto one and onto another, onto the other, the sum of those projections will yield the vector back. So what's projection onto the normal? Projection onto the normal is a simple thing. Given that the normal is a unit vector, and we have another vector to project onto the normal, the length of the projection will just be the dot product between the vector and the normal. That will be the length. That will be the length. And the direction will be in the direction of the normal. So an easy way to write it, now I will write v onto the normal. Maybe that's not great notation because we like reserving the space for the indices, but that's okay. Equals, well, let's see. I'll just use the letter v. Let's just use the letter v without any subscript. So v previously meant projection onto the tangent space. Let me think. I'm trying to think very quickly. Maybe another letter. Well, w. We'll call it w. I forget the choice I made in the book. So w. So v is the projection onto the tangent space. W is the projection onto the normal space. And of course, it's u dotted with n. That's the length of the projection. And now that we have the length of the projection, then that's the projection itself. So very similar to u dotted with s alpha, and then contracted once again with s alpha to get the projection onto the tangent space. Here, normal forms the basis for the normal space. So there you go. That's the projection onto the normal space. And notice this, that from this it follows that in components, this can be written like this. U, I, N, I. That's u dotted with n. I don't know if I've mentioned this before, but this is just the component of the normal. I believe I have written down an expression like this before, not just normal the vector, but its covariant component or contravariant component. And then, of course, we need to multiply this by the contravariant component. Covariant, right the first time. Contravariant component of n. And of course, messed up this. So I is used up by this relationship, so this contraction must be on J. Okay. So this represents projection onto the normal space. And well, that's all there is to say about the projection onto the normal space. Except that this object may now be interpreted, I'm just trying to be consistent, so I'll write it as Ni and J. Ni, and J can be interpreted as the projection operator onto the normal space. It should have the same property that applied twice, it is the same as being applied once. Let's just make quick sure of that because it can be so hard. So here it is applied once. Here it is, although parentheses are not needed, I'm just grouping them because I haven't given this a letter. I don't want to call it the same letter P. I'm going to call it Q. All right, it gets a letter after all. Q, I, J. So let's think about Q, I, J, Q, J, K. Q, I, J. Maybe as I'm erasing, most of you can already see what's going to happen. Something very similar to this. So Qij, Qjk. Such an elegant letter Q. I'm not sure why I hesitated. Equals N, I, and J, and J, and K, and Nj, because n is the unit normal. That, of course, is 1. So we're left with Ni and K. Let me highlight this. This is just the number 1. So we're left with Ni Nk, which of course is simply Q I K, just like we imagined. Okay, so that's the projection onto the normal space. Okay, and now the grand finale of the discussion about the projections. It's the fact that if we start with a vector, I'm writing this in components. I could have written this as vector expressions, but let's go right away for the component notation. And you find its orthogonal projection onto the tangent space, and its orthogonal projection onto the normal space, and you add the two, you will get the original vector back. So that's the property of projections onto two orthogonal spaces. I think it's intuitively clear that that's the case. And of course, let's recall that this one is, you will see that parentheses will be quite appropriate. Z I alpha Z alpha J U J, and this one is N I N J U J. That's why I put parentheses here. And this, of course, can be written, the left-hand side can be written as delta I J U J. And because the left-hand side and the right-hand side are identities for any uj, we have the following relationship. We have the following relationship. That, I'll write it in two different ways. That's Z I alpha Z alpha J plus N I N J equals essentially the identity matrix. These two singular matrices combine to give the identity. It can be written the following way, of course. This is trivial, but quite useful often. Zi alpha Z alpha J equals delta I J minus N I N J. So I don't know why, I think this is actually more elegant, but this is more frequently used in practice. It just seems to show up a little bit more. So I'll box this one. And I'll combine it with contracting the shift index on the ambient index, which of course results in the Kronecker delta. Two completely unrelated, not unrelated formulas, but formulas that say two completely different things. The bottom one being the relationship between the metric tensors, but of course because they both have to do with contracting the shift tensor, I wanted to put them together and box them side by side. Okay, this actually completes our discussion about projections and the shift tensor and its role as a projector and maybe a restorer of the ambient components given the surface components, and the relationship between the metrics in the ambient space and on the surface. And we will next talk about the normal, the components of the normal, and how to express them in terms of more basic quantities such as the shift tensor and the metrics. Okay, thank you very much. See you in a few minutes.